Hello everyone. Thanks for joining here today. Excited to see the community. So, I'm Mohit. I work with Amazon and I've been with the OpenSearch since the inception of the project. I work mostly in the areas of indexing, and I've been contributing more and more towards more areas around distributed systems and all. With me today is Tanik.
Yeah, hi everyone. I'm with Amazon OpenSearch since last 3 years. Primarily, I'm focused with monitoring and recovery aspect of managed OpenSearch service. So recently, I've also started contributing with in area of indexing as well. Now, Mohit will talk about the journey of derived source, which is very helpful for reducing the storage cost for a lot of workloads.
Yeah. Thanks, Tanik. Yeah, before we go into what derived source is and how it helps out with slashing your storage costs, right? Like saying slashing means that it's going to bring down a lot, so we'll need to live up to those expectations. Let's first try to understand how OpenSearch actually stores the data for any index. So whenever you ingest your data into an OpenSearch index, it creates multiple underlying data structures. For example, we have something like term vectors, which can be created when you want to understand what terms were created for a document. Then we have stored fields, which we'll cover later. We have something like numeric index, which is a BKD index, which is created within Lucene, and that helps you run point queries against numbers. So for example, when you want to get all the documents where, say, your latency is greater than 5 seconds or so, this is the index that would be the primary source for filtering the documents. Then we have an inverted index, which is your text index, where all the analyzed terms are kept, and from the term you know which document it belongs to, what's the position, what's the frequency and all. Then we have the columnar data as well, which is the doc values, and doc values is basically used for sorting and aggregation purposes, and it stores it's a columnar representation of the entire, basically the fields in your entire document. Then we have the vector data, which kind of deals with all the KNN related fields for you. And then we have the metadata and commit related files, which contain how a segment is structured in Lucene, what all fields are present, what are the field names, etc. Deleted docs and so on, and the commit points. So at a high level, OpenSearch will create a lot of this for you behind the scenes, and all of them come with their own storage costs, their own indexing cost and query cost, right? Now let's dive a little into what stored fields is. So stored fields is a format provided by Lucene, which OpenSearch leverages to kind of have a row-wise representation of the data. And when you basically have the data, when you actually want to fetch certain fields for a document, it's better that all of it is stored at a single place, so that when you want to actually do the retrievals, it's quick enough that you can do it in a single lookup. And from the structure of it, it's very evident that it's useful for the fetch phase of your queries, where actually you are going to retrieve the document's actual source or something. And how OpenSearch, or rather Lucene, stores it compresses all the stored fields that you provide to it. So by default, Lucene provides 2 compression modes out of the box. One is the best speed and the other is best compression. And best speed is tuned for better indexing throughput, but at the cost of not so good compression ratio. And then we have best compression mode, which provides you great compression ratios, but the indexing throughput can go for a toss. And between them, we have something called ZSTD, which OpenSearch introduced on top of Lucene stored fields format. And ZSTD provides you a good sweet spot for good indexing throughput and good compression ratios as well, and it is also tunable with multiple levels. Now, let's understand how OpenSearch uses these stored fields format, right? So the entire document that you pass to OpenSearch during your ingestion, that OpenSearch stores that in the underlying stored fields format. And other fields like the auto-generated ID or the ID provided by you, the routing params, all those go into the stored fields along with the source for a given document. And let's say you have also configured whether malformed field should be ignored or not. The meta information about that also goes to the stored field, so that during the retrieval you can leverage that information. Apart from this, you can, in your mappings, also set store as true for certain fields, so that if you want this field should be stored separately, that can also happen. Now, for the intents and purposes of this talk, the most important stored field that we are going to discuss is the source. So let's understand what source field is, right? So source field stores the entire input bytes that you would have provided to the during your indexing call through the doc API or the bulk API. And that document can be in JSON, YAML, CBER, and essentially OpenSearch will preserve the format and whatever bytes you provided as is. And on top of it, you can also choose to enable or disable the source field. Disabling the source field comes with the disadvantages which we'll discuss later, but can provide you cost savings. And also in the source field, you can choose what to include and what to exclude through the include and exclude filter, which you can again provide in the mappings. Now let's try and understand why source field is needed. Right, so as we already discussed, it stores the data in a row-wise fashion, so it's very efficient for hits retrieval for your queries. And you may have use cases where you want to actually transfer the data from one index to another, right? So there are use cases on reindexing where what happens is we search the data on the source index and we get the source back for the documents, and then we ingest that source into the new index. This is useful for cases when you may have to actually upgrade your indexes beyond 2 OpenSearch versions, where you may actually have to do reindexing. So for that purpose, without having a source, you won't be able to do any reindexing. Also then you have use cases around partial and scripted updates. So when you actually want to just apply a partial update to a document or run some script on an existing document to update it with the data that is already present, OpenSearch would fetch the source of the existing version of the document, apply your script or patch on top of it, and then create the new document with a new version. So for this also again source is needed. And the last use case is something which OpenSearch internally uses, is the Lucene-based recovery. So when you are relying on peer recoveries, for example, when you are adding a new replica for an existing index, in such cases, there are operations which get replayed from the primary to replica to keep it in sync with the primary as part of the bootstrap. And at that time, we use Lucene-based recoveries which rely on, again, the source field which is stored in Lucene. Now that we understand that source is needed for quite a few important use cases in OpenSearch, let's understand what footprint it comes with. So first thing I want to talk about is the CPU usage during your indexing, right? So whenever you are indexing, as I talked about, we compress the stored fields as well. So during your indexing activities, when the documents are being flushed to disk and the stored fields format is being persisted, at that time we actually run the compression and your documents actually get compressed, which consumes CPU, and it can go up to 20% CPU usage in certain cases. Also for coming to the storage cost, right? So for example, this is a pie chart which denotes a logging data that I analyzed it against. And the stored field is occupying almost 60% of the total index size, right? Like it's 2076 MB out of the total of almost 2900 MBs, right? So this is quite a large contribution due to the stored fields and specifically the source field that we store in OpenSearch. Now we already know that we already had a lot of data structures which we are creating, which we covered in this first slide. We had the inverted index, we had term vectors, we had doc values, kernel vectors, and also the stored input fields which you can configure. On top of it, OpenSearch stores the source as well, right? So what if there is a way that I can derive the source, regenerate it during the query using the existing data structures that I may have already created for my analytical queries, right? So coming to that, we have doc values, which already contains the values for a lot of fields already, and you can use that to get the value of a certain field, right? And if I can tie it back all together and create for all the fields, fetch the doc values somehow, combine them into a JSON, YAML, or whatever format the response is needed in, and then after stitching, return it back, I may end up not needing the stored field, right? Which is the source here. So for example, let's say you have an input document where you have a field A which is of type integer, and there you are adding a field like 1, 2, 1, 3, like you are adding multiple values for that field. Similarly, we have a field B which is date, field C which is a keyword, and all of them are getting translated into the columnar doc values. From these columnar doc values, I can recreate the source where I am able to recreate the value of A, B, C while I am going through the columnar structure of each of these fields, right? And given I have this, I may actually be able to eliminate the entire source. And just with this change, what we see is the size of the source or the stored fields format that was present in Lucene, right, from 2076 MB, it comes down to 330 MBs only. And this is equivalent to a 60% improvement in your storage cost. And it's almost like you need almost half of the machines which you had earlier needed in terms of the disk storage. Not only that, we have the performance improvement in terms of indexing and merges. Given that I talked about the indexing, the compression which happens during the indexing, all of that goes away, and now all of the work is in the indexing is happening only to create the actual data structures which are needed for your analytical queries. Similarly, for the merges, now that your segment sizes are smaller, right, because you're not taking the stored fields, or you're not consuming a lot of storage for stored fields, and you have also the lesser number of segments, the number of merges that happen become very less, which also improve the background activity that is happening on your compute, and hence give you more space for your other activities like queries and all. With this, I'll hand over to Tanik to talk more about how it was implemented and how as a user you can use derived source feature.
Thanks Mohit for covering importance of the source field and its footprint on the storage aspects. Now let's talk about how you can configure the derived source. So basically derived source is from the high level, it's as simple as that configuring the index setting. So you just enable it, and on the behind it takes care of everything, like it basically stops storing the underscore source field and thus reducing your storage cost. So now let's look at how like what all fields are supported. So it supports most of the field types that is being used as of now. So let's look at those fields. So we have boolean, then all the number type fields, then we have date and geopoints as well. So we have tried to basically provide the priority to doc values first, because it's easier to read the data from the doc values as compared to store field. So for all these fields, doc values are by default stored for analytical use cases. And in this one, for date and geopoint, for date we support all the format, so it will try to preserve the format that the user has provided in the final regenerated source. For geographical field types, we currently only support geopoints and not geo shape. So because in geopoint there can be lot of ingested formats like geohash, then point format. So it will basically convert it to lat long format, and it will give the reconstructed source there. Now moving on to more fields, we have IP, then keyword, scale, float, tags and wildcards as well. For tags, as we know, it doesn't make any sense to basically store the store field or doc values, because it's more of a, we don't support sorting and aggregation on the tags field, it's more of on the term basis. So that's why we only store field. So we regenerate the source from the store field instead of doc values there. For wildcard, it's not basically a traditional keyword or text field per se, because we basically first break it into substring and then create the term dictionary on top of it. So it's hard to derive the original value from there. So you will have to either enable the store field or doc values for that to be regenerated at the end. So now that we have talked about supported field types, now let's look at how it can be extended to other field types as well as plugins as well. So let's say you have KNN plugin and you want to support that fields for regenerating the source instead of storing it in the underscore source field. So you just basically have to override the methods that we have provided at the field mapper level. It's easier to do that way, and we already have support for we already have provided the utilities like regenerating the value from sorted numeric or sorted set or store field. So we just have to define like how it is supported for a particular field type and how to convert it back to the last desired format. Like let's say date field is stored as a long timestamp format, so you'll have to first convert it back to ISO format or user provided format. So those kind of implementation you will have to do. Other than that, it's very easy to extend it to the field types. Now let's look at the how interface is defined, and those methods are defined in the field mapper level. So we have primarily two methods like can derive source and derive source. You just basically define like for what all field mapper types it is, or mapper type it is supported. So that is inside the can derive source function, and in derive source generator we basically define how to regenerate it back to the original format using multiple data structures like doc values and stored field. So using that, like extending these methods, it can be extended for other field types which are not supported as of today. So now let's look at the flow of create index path. So let's say we are trying to create or update index mappings. So it will basically try to parse the mapping first, and then for each of the mapping fields it will call the derive source can derive source method to check the feasibility of having if it is supported for derive source or not. So it will iteratively call for each of the configured field mappers, and for those of field mapper it will return back the response to user if hey this field types are supported, and it will be able to create the index. Otherwise it will throw an exception if a certain field is not supported. Let's say for wildcard, if you are not configured stored or doc values at true, then it will throw the exception. Now let's look at the search path, how we regenerate it back to the document. So basically during fetch phase we will know that what all documents needs to be returned for top hits query. So it will, for each of those documents it will call each of the subfield mappers which are defined for that index, and for each of those subfields it will regenerate the source using respective data structure based on doc values or stored field using those utilities that we have, and it will give the final resulted document in user provided content type. It may be JSON or YAML, anything. So yeah, now we know like how it is supported under the hood for most of the field types. Now let's look at some of the challenges in terms of search performance or recovery aspect. Now let's look at about search result. So while we know that while regenerating the source it goes through each and every field's doc value, and then it combines back the final result. So for that it will have to go to the different disk location, and it may end up using more number of disks as compared to source field, which would be at a single place, and that would be easier as compared to reading the doc values for more number of fields. So we might see the latency there when fetching the large number of documents, because in most of the cases by default we return the top 10 hits, so there we are not seeing any performance issue there. Whereas in some cases we have seen performance improvement as well, because now we are reading the aggregated doc values from a small number of small size shard or small number of segments. So but let's say you are fetching the 10,000 documents like or doing the scroll query, you might see the latency increase there. So and for doc values we know that it doesn't require decompression there, because it's directly a map, and mostly it will be fetch from memory instead of file. So that is the case with source field. We first have to fetch it from the disk and then it gets decompressed. So there is a CPU cycle loss as well. So in most of the search workloads we have seen we have not seen any degradation per se. So now let's move on to let's now move on to recovery aspect of the performance. So there are two type of recovery. One is file based recovery and one is operation based recovery. So file based recovery can be much faster given that there are lot less number of segments, and those segments are also very small in sizes compared to normal flow, because now we have removed the source field which was taking the significant amount of space. So in operation based recovery there are two flavors to it. One is loosening based recovery and other one is basically translog based recovery. So in translog based recovery we might end up seeing in loosening based recovery we might end up seeing degradation, because now you allow to reconstruct the source from different location and it can take times for a lot of document. Similarly for translog based recovery also we might see this, but we have a way to bypass that because in translog based recovery we have the original source with us, and if you want to have similar experience as deriving the source from segment, you will have to basically first ingest those temporary source from translog to in-memory buffer and then derive the source on top of it, so that final output in terms of display looks as similar as that while reading it from the segment. To basically change this behavior, it can be disabled to gain the latency when fetching the source from translog or doing the translog based recovery, with the caveat that it will have original source and while reading from the segment it can have a derived source. So it is also behind the index setting. So now let's look at some of the challenges in terms of supporting different type of field types like keyword. So as we know, a keyword has by default doc values enabled, and with keyword there are mapping parameters as well, like ignore above, normalizer. Those parameters, let's take an example of ignore above. In most of the case you might see that it's configured as 256 length. Whenever the value of the field value is above 256 length, basically we just skip that field value and we doesn't store it in the doc value. So in the search it's you won't see while doing the term aggregation. And similarly for a normalizer, it changes the original value of the field to the respective normalizer. Let's take an example of lowercase. It will basically change first, replaces all the character to lowercase and then store it to the loosened doc value. So we will lose the context of what was the original value at time of ingestion. So for this kind of mapping parameter currently we don't support keyword as of now. For such cases you can always enable the stored field for that particular field where you want to configure these mapping parameters. That way we'll be able to support the derived source for those fields. Now let's talk about most commonly used field, which is text field. So for text field we know that its doc value are by default disabled, because it doesn't make sense to have doc values for text field, given that we don't support aggregation or sorting based on text field, and it's only based on terms aggregation. And for text field we also store only inverted index in form of posting and frequency. So using that, it's very difficult and expensive to regenerate the source. So instead of that, we have implicitly enabled the source field for the text field, so that we are always able to reconstruct the source using that. Now let's talk about some of the mapping parameter limitations which we have as of now. So we have copy to field, which we know that it copies the value from multiple field into the one field where we have configured this parameter, and because of that we actually lose the actual source context in the doc value, so it's difficult to reconstruct that. And for similarly we have null values, which basically replaces all the all the documents with a null value wherever with the value that you have defined in the null value, and let's say you configure null value equal to x for all the fields having null value, it will replace the doc value with x value. So we don't know like what all documents had a particular field null while ingestion, so that complexity is there. For nested field also we simply don't support derived source as of now. And in previous example we saw, right, we have doc values can be in two forms, sorted numeric or sorted set. In sorted numeric, it basically sorts the order of, whenever there is a multi-value field, it first sort the order of the content and then stores it in the doc value. Similarly for sorted set, it removes the duplicate and sort it in it and stores it in under the doc value. So you might see this variation in the final reconstructed source while using multi-value fields. Now I'll hand over to Mohit for talking about like where are we and what are we planning next.
Sure. So yeah, as Tanik talked about the implementation, I think all of the levers that you now need to use OpenSearch derived source feature are in place, and this feature is now launched with OpenSearch 3.2. It's the first release of the feature, and we have implemented most of the fields that we thought were most common for use cases around log analytics and observability. And we are still working actively on adding support for more fields, on more performance improvements, and reducing the limitations that we talked about. So immediately in the next that we have is support for fields like range and geoshape. We are also looking on how we can optimize the overall document retrieval by taking advantage of how doc values are actually stored on disk and what is the access pattern for them, and based on that access pattern if we can leverage the same to generate the source. So we are trying more and more optimizations around that, which should help us bring down the retrieval time for your document source further. And that is something we are actively working on, and we'll have something out very soon. Again, on the recovery speeds, like as Tanik talked about, that operation-based recoveries can be slower. So we are looking into how we can work more around batching and the same around the faster document retrieval, which can help us improve the recovery speeds that we see today. So with all of this, we should have basically more advanced representation of this feature, which should again improve this further from the state it is in. Yeah, and I'd also like to thank the entire community and the folks who helped us with the delivery of this feature and helping us get it out in OpenSearch. And yeah, I've mentioned a few folks, but it was a lot beyond this, like the constant feedback from the community and everyone, which helped us deliver this. With this, yeah, I'll open the floor for any questions. Okay.
Do you guys do the search benchmark to see what's the search performance outcome with the derived source?
Yeah, so we compared it to LZ4. So the question is like, what was the impact on the search performance? And for most of the use cases, when the number of hits are fairly moderate, we didn't see any regression in terms of the search latency. But when the number of documents that are getting returned as part of the search query, we saw some regression which could range from 10% to 100% in terms of search latency. But that is when compared to LZ4. Compared to best compression, like where the decompression itself takes a lot of time, there it was in the same ballpark as basically the retrieval of source. Yeah, I think we'll soon publish a blog which would highlight more on the search performance, indexing performance and everything, so that should help you more. Yeah.
Then do we have some recommendation when to use the right source online based on the search use case?
So the question is,
Not
yeah.
to use it because certain search performance customer care about.
Correct. So the question is when recommendation around using the derived source feature with respect to your impact on search performance, right? So ideally, yeah, it can regress in certain cases given the source regeneration is happening. So when you are very sensitive about your search latencies, I think in that case, you may be better off relying on the source which is stored with the best speed algorithm so that your retrieval is faster as well. Because this does add some latency, and also when you are doing heavy updates, heavy scripted updates or partial updates, right, which can happen in search use cases which have like catalogs which are getting continuously updated, there may be some impact in the performance. So in such cases where the basically latency of the document retrieval is, you are very sensitive to it, I think in such cases it's better to still continue using the original source feature, but for use cases around log analytics, observability, this saves a lot on the storage with the same search performance almost. Okay.
You mentioned about the penalty of having more disk reads in a reconstruct. For each of the columnar fields, do you actually maintain a single file or separate blocks of data?
So in Lucene, it's a single file, but the data is stored in basically sequence for first one field first, then so on and so on. So it's a columnar representation, right? So you have to actually, for let's say for document A, you want to get 5 different fields. So you may have to go to different blocks in the disk to fetch that out. So yeah, around that, we already have a performance improvement. Like if instead of going doc by doc and then getting each field for that doc, we go field by field and then keep marking the document visited so that for a field we just complete it and don't have to come back again.
So there is no way to logically control the order in which the fields are being stored on the disk.
Yeah,
The reason I'm asking this basically is you're familiar with most databases like HBase. It's columnar, so each field is technically a columnar field.
Correct.
But they have also a columnar family. And so we basically logically switch columns kind of are typically accessed together. You want to bunch them together in the disk at least, so that way your access is far less because you're not now jumping across blocks. You know, a couple of fields which might be logically, your document might be apart but being accessed during the retrieval together. You have a control over putting them together in your disk.
Yeah, I think unfortunately how Lucene structures it today, the one we rely on is fully columnar. I think what you're talking about is a form of a hybrid, right, where rows and columns are chunked in some ways.
So for example, you could have columns A to Z, but in my retrieval, when I'm doing reconstructing the document, the right sources, I only care about A, D, and G. So if I have a control where I can see that A, D, and G should typically be together on the disk, then I have better control because my reads should be less. Else I would jump for A's values, then skip 3, then go to D, and so on.
Yeah, today in the structures that we have, that doesn't exist, but yeah, that would be a good add.
This performance, that's one thing you can do.
Makes sense. Makes sense, yeah. Yeah.
Actually, I have a counter argument towards that. That only works if, let's say, the results are more like you're fetching a large chunk of results, right? So that they are close to each other, so that you can.
True, but you're required for the disk eventually versus having to skip block. Maybe in today's game, SSD doesn't matter so much. But typically, if you want continuous reads, the sequential reads are preferable over random block jumps.
Yes.
So yeah.
I have a question regarding this, how we set up the benchmark and performance. The reason is being, okay, you're storing this derived source on disk, and Linux will try to ping to me when needed, so that I'm already doing a benchmark. Is what percentage of those this derived source is actually read from or to memory, from memory, and what percentage is actually read from disk. So are you seeing that actually the disk I/O is actually increased a lot because you switch to this derived
So I think, so one thing is that the stored fields that we use, the format that is, OpenSearch never maps it, like it doesn't use virtual memory for it ever. But for the doc values, we do use that. So with this change, we are able to leverage to basically fetch what's already present in your virtual memory. So that exists, and in terms of benchmark, like the page thrashing and all, I don't think we have that exact number. Mostly we analyze it from a level of how it behaves in basically when the same compute and resources are available to both the structures here.
And the second question is that this still sounds like this is, I mean, this is the OpenSearch related, but not the technically user related. So that, so if I have a face of the index, we can also use this feature, right?
Yes, yeah, definitely. I think we just need to extend it in the field mappers corresponding to it in the plugin, which is providing the file structure, and then it should be usable.
You mean some further development is needed something?
So you mean for the vector files, right? Yeah, I think there is already one feature which is present in the KNN plugin around derived source, which is already available to be used, I think, since OpenSearch 3. For it to be used with the same setting and all, I think, yeah, there is work needed so that we can converge both the approaches and it can just work with a single knob. That work is still needed, yeah. Cool, so if there are no more questions, thanks folks for joining today. We'll be available outside the room for any questions. Thank you.
Yeah, thank you everyone.